A L-shaped bracket of circular cross-section is shown in the figure. We have A to B, it protrudes 2 meter from the fixed wall, and then it has a horizontal bar of length equal to 1 meter. At point C, vertically downward load is acting equal to 10 kilonewton. The diameter of the bracket equal to 100 mm. Maximum normal stress at point A you have to calculate. So observe here what is the effect of the force 10 kilonewton here. First of all, we'll shift the force from C to point B. So since if we shift the force from point C to point B, we have change in the line of action. So third time we are doing the same thing, that if the force is shifted, then the magnitude of the force is remain same, and in this plane the moment is generated. This moment is parallel to the given cross section, so that will be called as torque, and the torque will be same as equal to the force multiplied by the length equal to L1, which is equal to 1 meter. So step number 1 here is to shift the force from the point C to point B. According to the rule number 1, the force will remain as it is. There is no change in the magnitude and the direction. So same force you have to show at point B, that is in the second figure, and it will act vertically downward. So the magnitude of the force is remain same, that equal to 10 kilonewton. In addition to that, the moment is developed about the point B, and at point B we have moment is same as the torque. So the moment will be F multiplied by L1, and L1 equal to 1 meter. So in this case we have total torque T will be equal to F is equal to 10 into 1 is 10 kilonewton meter. And this torque is produced in a clockwise direction. So we'll show here clockwise direction, and we can represent here the torque in this plane will be clockwise, and this one is the torque, and this torque is same as equal to 10 will be kilonewton meter. Because of the force here, the bending will produce, and if the bending will produce, the maximum bending moment will be at the point A. In that case, we require the length L will be equal to 2 meter. So let's say we have length is equal to 2 meter. So 2 multiplied by F will be the maximum bending moment at point A, as well as the shaft is subjected to a torque. Again, the shear stress due to the vertical shear force will neglect. Only the effect of the bending and the torque will consider. So in this case, the shaft is subjected to pure twisting moment and the bending moments. We'll calculate here the equivalent bending moment, and using the equivalent bending moment we can calculate the maximum normal stress. So we know that the equivalent bending moment is equal to ME is equal to 1 by 2 into M plus we have under root of M square plus T square, and this value of equivalent bending moment is given as pi by 32 for circular shaft is D cube multiplied by maximum normal stress. Now only thing that you have to calculate here the bending moment at A. So bending moment at A will be same as equal to MA equal to force multiplied by length L, that will be equal to 10 multiplied by 2 is equal to 20 kilonewton meter. So M value is 20, torque is equal to 10. So we can solve this and we can find out the value of sigma max. So we have 1 by 2 into M is equal to 20 plus we have under root of 20 square plus 10 square. This value is in kilonewton meter, so we'll multiply by 10 to the power 6 is equal to pi by 32 into D cube, and we have diameter is given as 100. So we have 100 cube, and corresponding value you can calculate as maximum normal stress. So the maximum normal stress, that is the principal stress, will be equal to 215.85 megapascal. A machine frame is shown in the figure below is subjected to horizontal force of 600 Newton parallel to the Z direction. The normal and the shear stress in megapascal at point P you have to calculate. In that case, you have to shift this force to the point here. Let's say this point equal to B point and this point equal to A point. So first you have to transfer the force from point B to point A. Since here the line of action will be changed, so the force will be shifted as it is, and one torque will be developed at point A, because in this plane here the torque will be developed by the force F. So we will show here a vertical bar A to P, and our diameter is given as 30 mm and the length will be equal to 300 mm. Let's call this force is equal to F, and we have this length equal to L1. So when the force is shifted from point B to point A, the force will remain same as it is. So you have to show the same value of the force along the Z direction. So this will be the same force is equal to F equal to 600 Newton. And this force above point A will make a moment, that will be the torque. In this plane you will observe the torque, and that value is given as F multiplied by L1. We have F is equal to 600 and we have length is equal to 500 mm is 0.5. So in this case we develop a torque equal to 300 Newton meter. Direction of this torque will be anti-clockwise. So in this figure we will show the torque in an anti-clockwise sense. So this torque T will be same as equal to 300 Newton meter. Now this force is acting perpendicular to the axial shaft, will produce the maximum bending moment at point P. So one bending stress is produced, that will be the normal stress, and one shear stress is produced. So the force F will produce here the maximum bending moment. So we have maximum bending moment is M, is produced about the point P, is given as the product of force multiplied by length. So we have force multiplied by length L. In this case we have force is equal to 600 Newton and we have length equal to 0.3. 600 into 0.3 will be equal to 180. That will be Newton meter. And the same torque is available at point P also. It means that the point P is subjected to one bending moment and one twisting moment. So two stresses are produced at point P. One is a bending stress and one is a shear stress. Bending stress will be treated as a normal stress and shear stress is due to the torque. So two-dimensional state of a stress is shown at point P. One normal stress is produced 32 times of m by pi d cube, where diameter is 30, and one shear stress is produced that equal to 16 times t pi d cube. So let's calculate here the shear stress equal to tau xy. This value of tau xy is same as 16 times t divided by pi into d cube. So we have 16 times, we have torque is equal to 300 Newton meter. So we have 300 multiplied by 10 to the power 3 and is divided by pi d cube. We have pi, diameter equal to 30 cube. So the shear stress tau xy will come out to be 56.6 megapascal. Similarly, the normal stress is given by sigma x, and we have value of sigma x is equal to 32 times m by pi d cube. That is, we have 32 times. Bending moment m is 180, so we have 180 into 10 to the power 3, that will convert meter into mm, is divided by pi and diameter equal to 30. We have cube of it. In this case the normal stress produced is close to 67.9, that will be megapascal. Normal and the shear is 67.9 and 56.6. Choice A is correct choice. A machine element XY fixed end at X and is subjected to an axial load P, transverse load equal to F, twisting moment equal to T at its free end Y. The most critical point from the strength point of view is a point on the circumference at location Y, that is on the circumference means this point or this point, or a center at the location Y. Center means this point. Or a point on the circumference at a location of X, that is this point, or a point at the center of location at X, that is this point. So P will develop here the normal stress, F will develop the bending, and T will develop the shear. In addition to that, the value of F, if applied at the section X, will also develop the shear. But even that value will neglect here because its magnitude is very small. we'll only consider the effect of P, effect of bending at point X. So we have bending moment at the given section X will be equal to F multiplied by L, whereas the bending moment at point Y will be equal to 0. So no bending stress is produced at Y, only the bending stress is produced at X, and that too on the outer fiber. Because of the force F, the cantilever will bend in this way. So this is approximate profile I am showing you. I want to just show here that which one is compression and which one is tension. Naturally here the shorter member with the inside will be compression and the outside is tension. Since we are interested here the circumference and the center at location Y, so naturally here the bending stress at this point that will be equal to 0. So the critical section will be either at center or either at periphery. So the contraction of the bending stress will be 0 at Y, so we will not consider this is a critical loaded, but we have maximum bending moment will produce at point X. So we have to show here the bending stress, then we'll show one normal stress and one shear stress at this point, and we'll show here which one is the critical. So we'll show our distribution about the section X, and this one is a circular cross section. So we'll consider here one point A exactly at the center, and one point B will be on the circumference, and one point C is also on circumference. First I will show the bending stress. Bending stress for the top will be in tension. This will be neutral axis. For neutral axis bending stress will be 0, and at bottom we have compression. So bending stress positive will show rightward. So this one is the maximum value of the bending stress sigma B max corresponding to point B. At point A we have value of bending stress will be 0, and corresponding to point C we have compressive stress but is a maximum value. So this one is the effect of M, and this value of bending stress is same as equal to 32 times M divided by pi d cube. For circular section we have 32 M by pi d cube. Next we'll show the effect of the shear stress. Shear stress will be maximum at point B and will be 0 at A. So I have to continue with this diagram here, and we'll continue with the location also. And the maximum value will be at point C. So let's represent like this. So we'll show this value is the maximum value of the tau max. And this maximum value of the tau max is same as equal to 16 times T by pi d cube. So I assume here the torque is acting in the same direction, and therefore here we have shear stress is acting in the opposite direction. But as far as the shear stress is considered, the shear stress will be 0 at point A. And one more stress will show as a normal stress. This normal stress is uniform over the entire section. So its magnitude is remains same everywhere. So this one is same as the axial stress produced due to the force P. And this value is remain constant for all. So this one is the axial stress produced is P divided by circular cross section. So if we develop the state of a stress for point B, which is on the circumference at section X, so at this point we have to show two stresses. One is the shear stress and one is the bending stress. So this will be the bending stress, that will be sigma bending maximum, and one value you have to show as a shear stress, that equal to tau max. And if you consider the center point here, which is the neutral axis, that is A, at A we have only one stress is acting. There is no shear stress, no bending stress, but we have only one normal stress. So this value is same as sigma axial. And at point C is considered, we have shear stress is to be shown and the bending stress is shown. So it means that at point C we have to show the two stresses. So let's show the state of a stress for C. The bending stress compressive in nature. So this value is compressive in nature. So you have to show the inward arrow is same as sigma B maximum, and we have shear stress is to be shown in the opposite signs. So this one is a shear stress, that is same as equal to tau max. It means that a critically loaded will be either B or either C. So B is a critical section or C is a critical. So the location of Y is entirely wrong. and a point on the circumference at a location of x, that is a correct choice. So both these points B and C are on the circumference. So here B and C are on circumference at a location x. So choice C is correct. So failure will be either at B or will be either at C. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.